very good what they need to do in order to analyze the data. So I have to be good starting now. Got it. Tried and true. So, they know what to do, but every once in a while something happens in the middle of the night. Things go bump, and you want to understand some effect or something that you're seeing, and you have to write code in the middle of the night that runs on this megahertz data stream to understand what's happening in your experiment. On top of that, once the data are taken, you have to analyze it, and you don't want it to take years and years and years and years if you can help it. And so the development cycle has to be fast and flexible. And finally, you don't want to close the door. We basically went from here's a USB stick on your laptop to here are the keys to a supercomputer in the span of a few years. Most user groups who are doing science are not prepared for a leap from USB stick to supercomputer. And so we're trying to make efforts to alleviate some of that pressure, make things as easy to use as possible, or as easy to use as necessary, I guess, so that you don't have to mount a significant computing effort to get there. So the upshot is, and this is like a wide variety of experiments that need to change their analysis in the middle of the night, and we have to be able to accommodate all of that, all while tackling the data acquisition problem. We have to collect the data in the first place. So just to kind of put this in context, from proposal to data deletion is a 10-year time period, and we're responsible for that data. The facility is holding on to that data for the user. And this is repeated for hundreds of experiments every year. So, the proposal comes in, it's allocated beam time. There's an experiment planning process that takes weeks to months. And then that data generation, data collection cycle goes through 5 days of shifts. And, this cycle of generating data, feature extracting it, doing some sort of visualization or interpretation on it, feeding back to the experiment to tune it better, happens at the sub-second level and the second minute level and the hour level during that beam time over and over and over again. Sometimes there are less than 1 second control loops happening and, minutes long and hour long control loops happening. So this cycle is repeating over and over again. And then that, time to publication is actually something like 3 years. It takes a long time to write a paper to analyze data. So that we have to be able to access the data and analyze it 3 years later. We have had publications on 15-year-old data. So, we have to be able to have a system that can handle knowing what the data format was back then and what the analysis was and all that. So just wanted to give you a sense of the timescales we're talking about here. And so we built this system, and here are the strategies that we have employed so far in order to deal with the high data rates and the data collection problem. First is do more with less, meaning reduce the data on the fly, and ideally do feature extraction on the fly because you can steer experiments with that. When you do data reduction on the fly, it has implications for the data format. It means you're now sending a bag of bytes. You're not sending a frame. You're sending a bag of bytes. At all costs, keep up with the data rate. Analyze the data at the rate of production so you can monitor the data quality, validate that data reduction. In order to do that, you need performant and scalable software. That is also hiding the complexity of that from the user. You want to seize the means of data production. So by this, I mean you use that actionable information that you're producing from these feature extracted data to actually steer the experiments and do the right thing. Where necessary or possible, you can use AI-assisted decision-making to help you decide where, what data to take next, so that you take only the data you want, none of the data you don't want. And the upshot is that we are running algorithms at every layer in this pipeline. So these are the detectors over here. These are the compressor nodes. There's some nodes here that let us do a veto. And this is the first layer of base cache where we write the data, and then offline storage and offline processing over here. Every layer from the detector, the compressor nodes, you can do data reduction. You can run different algorithms for different purpose, and they have to be tuned to the latencies and basically the hardware and the software that resides in that layer. We do have this integrated hardware software infrastructure. We have local resources in the SLAC Shared Science Data Facility, the S3DF, and we try to use the Super Facility API to get seamless access to remote HPC resources. I say seamless. Seamless is the ideal. Right now, it's still somewhat high touch, but it's getting a lot better. We do use this in anger, so we do have access to these resources at NERSC and at Oak Ridge and at Argonne. We have tools to do workflow orchestration, and something that I'm not going to say a whole lot about, but that is very important, is that our data is a national resource. It is being viewed as such. And so data curation and data management of this of our data set is very important. And the goal is to generate analysis pipeline ready data products as we collect the data. We're not there yet, but we are putting together the pieces, and the long goal is to get to that point where you're just generating data products and automating the metadata collection so that we can find that data, and then once it's found, make it usable. All right, so this is what the pipeline looks like visualized. So data is flowing from the left to the right. So there's the X-ray hitting your sample and then striking the detector. On the detector, there are ASICs and FPGAs that can be programmed to do things. At the moment, they're programmed to move bits from point A to point B, but they can be also programmed to steer things, make decisions, veto data, or feature extract data, or compress data. At that level, your latency is about micro to milliseconds, but you have very little. Get into it. Then the data passes into the data reduction pipeline. That is a CPU GPU layer. There are lots of compute nodes there, and there you can run considerably more sophisticated algorithms, although you still have to keep up with this megahertz data rate. And so there you're looking at like seconds to a minute, seconds really of reaction time. Once you move to the offline analysis, that can either happen locally on the S3DF. That the S3DF is the landing pad. That is where the data sits, and then it is transferred off somewhere else if it needs to go somewhere else, or we use local resources to analyze it. But there you basically are in the infinite compute approximation, and you can do whatever analysis you want, provided your software scales, and you can get your data there. So those two things have to be satisfied in order to do it. So we have a heterogeneous pipeline. The upshot, we have ASIC, FPGA, CPU, GPU, and the potential to put in other accelerators. If they, prove like useful, we can do that. And we have a wide variety of hardware in play on the offline analysis side. Just touch the screen. Okay, and so these are the sorts of algorithms that we run, in these various layers. So there's the experiment control and feedback is happening as close to the detector as we can get. It's either in the green or the yellow layer. It's either DRP or closer to the detector. And then in the offline, the things that are suitable for offline are the things either that scale really, really well, like the real-time analysis, when you want to stream data out, a lot of data out, and then analyze it with a lot of compute, and then return results in near real time as you're taking the data. You can do that. We do that with the NERSC. Or you can do things that are of slower time scales that bring together a lot of computing or a lot of data, like multimodal analysis or simulations, sometimes large scale model training. We've done that on Summit and Frontier. Rapid model retraining we've done at Argonne, and knowledge distillation. So when you want to move something from the offline to the online, you can make a big model much smaller. And for those, we use these big supercomputing facilities. So a few words about life at the edge. Okay, there we go. So I'm gonna, this is if you want to know more about this, talk to Ryan Coffey. He'd love to tell you lots about it. But this is a time series, so we're looking at digitizers here, and the upshot is that you can push machine learning using a SLAC neural network library into FPGA or into an accelerator and do inference at very high rate in order to do experiment steering or to produce this feature extracted data. It turns out that the raw data rate is something like 200 gigabytes per second, but once you reduce the data, it's 2 gigabytes per second or less. So it's quite good data reduction. The accelerator can feed off of this instrument. And the upshot is that we have this problem that we want to be able to do inference at the edge, but it needs to be programmable, still needs to be adaptable. And in addition to ASIC and FPGA, it's possible we might have some novel accelerators there for doing that inference. And if that were to happen, we have to be able to accommodate it, to absorb it and maintain it over the 15-year life cycle of the data. So, that is a unique challenge. We are trying to push data into the detectors themselves. So push computing closer to the source. And there are various projects, including the Arraeus one and SparkPix, and there have been a number, and AISDC. There are a number of projects to try and push things into the detector itself. So these are the big imaging detectors. And what I wanted to point out here is that it's great when you can have data reduction on the detector. It solves a lot of transmission bottlenecks, less data comes out, and you alleviate a lot of network storage and computing bottlenecks. But the closer you get to the detector, the less of the actual detector you see, make a decision off of. So you're seeing only that little colored box up there at the ASIC level. And so the kind of data reduction you can do there is usually very, very limited. It's like region of interest, bit level compression, or event-driven kind of stuff, spatial sparsification, something based on energy, but very difficult to make a decision about what's happening in the entire plane of the detector based on that one little piece. The FPGA level, you see a little bit more, and there's some spherical symmetry here, so maybe you can start making decisions, okay? And then once you get out to the data system or to another edge processing layer, which is a form of FPGAs, then you can start beginning to aggregate pieces of the detector so you can make a bigger decision. So your versatility goes up the farther out you go and the more computing is available. But the ASIC and the FPGA level is still desirable because it solves a lot of these transmission bottlenecks at the detector. We've also done, trying to put ML in terms of AI classification of images for vetoing, for Bragg peak finding, and we tried to put that with some success into FPGA. And then once you actually create these machine learning models at the edge, you also beget new workflows that themselves require significant computing in the offline. So in order to build those models that have the flexibility and the adaptability we need to do large scale training to build the model in the first place. So we have to go to Oak Ridge to do that. Or we need to retrain on streaming data. So we have to be able to stream raw data out to Argonne, retrain really, really fast, send new weights back, update those weights while we're in the experiment. And if we have models that are too big, we have to make them fit into the itty bitty living space of an FPGA or an ASIC. For that, you need knowledge distillation or some other tools. It doesn't have to be knowledge distillation, but you have to compress the model and ensure that it has the same performance. So heterogeneous pipelines do support all of these time, data, and compute intensive workflows, but they often generate their very own computational requirements along with it. So going into the DAC and data reduction pipeline. So the data reduction pipeline is implemented on a CPU, GPU layer. We've implemented a number of algorithms in there. They are experiment technique specific. They mitigate these storage computing bottlenecks. We have a way of aggregating small bits of data from all of the compressor nodes so that we can make a decision, a veto about the whole event so we can see a whole picture. We can't do that for all events and all things. And the important thing is that we save the reduced data and a version, some fraction of the raw data to allow us to verify what's happening. One thing to say is a lot of these data reduction algorithms are developed offline, and then they're moved out and migrated online. So portability is very important there. The way we've implemented the GPU pipeline, this is a work in progress. Okay, there we go. Is we have this super server chassis. So this is what the hardware looks like now. So I should say that the big imaging 4 megapixel 35 kilohertz detector that we're putting into XPP in January, sometime next year, produces some 280 gigabytes per second that have to be analyzed on the fly. It has 240 some fiber pairs. So that's a lot of fiber pairs that are coming out of this detector. So the same problem we have with dealing with large data, they also have in getting that data out of the detector itself. And so we first have to handle these like independent panels of data coming into this GPU. And we have to get them into a GPU so we can do some processing on them. So we have the super server chassis, which has 12 slots in it. that we can fill with FPGA boards, which can take 8 fiber pairs each, and then put in some GPUs, and then we can adjust the ratio of FPGA to GPU to suit either throughput needs or performance needs. Our worst case right now is a 16 megapixel at 35 kilohertz, which is 4 times as many fibers as that. So it's a huge problem. And one other thing I should mention is that some of the detectors read out at a much lower rate. So some of them are reading out at 35 kilohertz or 40 kilohertz, and some of our detectors are reading out at a megahertz, and some are reading out once per second. And somehow we have to timestamp align all of them. And some of those detectors that integrate, we have to be able to match up with exactly the pulses that came while it was integrating. So it's a complex timestamping problem. All right, the GPU readout data flow kind of looks like this, where the timing, the detector, the accelerator tells us when a pulse is going to come down. That's the timing system. That's that timing fiber up there. And then it gets distributed to all of the panels on the EPIC UHR. That's the name of the camera. Each of these panels sees 6 ASICs, and that's that many pixels per ASIC. And then the fibers go into the FPGA. And then over PCIe, we do this distribution where we take the data that's coming in over FPGA and we deliver it to a GPU core. And then it processes the data. So it takes its little chunk and does whatever it needs to do to that chunk, and then passes it on down the line to another piece of software that does the time ordering, file writing, and either writes to XTC2 or sends information back to a trigger. There's a CPU also on that chassis that can say, okay, veto the event or keep the event. So some of the things we do, event build is quite minimal. For the veto, we use libfabric to abstract out between LAN and Ethernet differences, and we try to do zero copy to the extent we can. Can't do it completely. This is just a word on performance and complexity. So just so you're aware, our data looks like this when it comes off the detector. With corrections that are sitting on a disk in a file, they start to look like this. This is what you want to analyze and make a decision on, not this. So you got to do all of these corrections, which means you have to get the information that's sitting in a file in the offline system somehow into here for every single event. Isn't it lovely? So one other word, you have to monitor all of this. So we have a piece of software called AMI, Online Monitoring, that can take data and distribute it out to a bunch of worker cores so we can visualize what's going on. And there's a GUI that you can use to basically visualize what's happening. And it runs on a statistical subset of the data. It's useful for visualization, and this is what it looks like. But it's a lovely piece of work and very, very useful for looking at the data as it's coming in during the experiment. I mentioned before, why do I see something different than what you see? Okay, there we go. That we have a custom data format. So the format is identical in memory as it is in storage. So it's the same on the wire as it is in memory and in the file. And that allows us to run our analysis framework pretty much everywhere. There's no serialization, deserialization step compression, and it has a natural support for the fundamental types like integers and floats. And we have ways of decoding what software was used in order to encode the data so that when it's the opposite side, you can decode it and know what it came from and what bytes mean and how to interpret them. We do separate small metadata from the big imaging detectors so it can be read more quickly, and that lets us do the event build offline. And we try and keep a Python interface so that it's easier for users to use. And then it supports variable length data. That's kind of what it looks like. It has a header that has a timestamp and tells you what the data is. And then it has some other pieces of information inside, like type of detector it was, whether or not there were any missing pieces, and so on. And then it tells you how long it is and payload is there. And you can nest these, and it's a very nice format, but it's not user friendly. It's data system friendly. So on top of this, we have an analysis framework that can access that data and then turn it into something that the users prefer, like HDF5 or whatever data format they like. PSANA uses MPI to overlap I/O and compute and try to do portable performance on new architectures. It employs a perfectly parallel pattern where every CPU or GPU core gets an event to crunch on. And I think, we have, there are limitations to that, that makes a lot of things easier, but it also makes a few things harder, which I think others will talk about. So it is perfectly parallel, memory management largely done with Python. There is this small data that's defined by users for what's useful for filtering the data offline. And so we write that file, and then that makes it easier to do the event build and to create the new data format that the users want. We try to hide unnecessary complexity from users. So we have this MPI parallelization and HDF5 production and detector corrections that happen under the hood. And we have support for integrating detectors, for analyzing data while it's being written, for jumping to selected events, and the ability to use Grafana to optimize the performance. So I'm almost there here. One bit of complexity, so this is in the generation now. We started out with these XTC files, right, XTC data, and what the users really want is HDF5 with event-built images, fully corrected, and so on. And it turns out that in order to do that, you have to read a bunch of stuff from files. And reading from a file is actually really hard, and does, there's a lot of bottlenecks there. So to get rid of those bottlenecks, we have PSANA does a lot of MPI magic under the hood to try and read from the small data, take batches of time sorted data and allocate it to big data nodes, which then can crank through the analysis and then write the HDF5. And there's some tunability here, and it's great. It hides all of this complexity, but it uses MPI, and then any user workflow that builds on top of it, that thinks it can control how these tasks are distributed across nodes using MPI is likely going to have a bad time in their scalability, because PSANA says, no, I'm going to control that for you. So I think there's a limitation here that we are encountering now. One way around that limitation is the use of LCLS streams. So this is a new piece of software that developed by Valerio in our group and some people at Oak Ridge, David Rogers. And so the stream data is kind of reduced. We try and do some of this local PSANA stuff and then send only the data product in the format that's desired to the remote site or to a local site. And so it kind of, only the relevant data gets transferred. So if there's data you don't care about, that doesn't get transferred. The stream data is pre-processed, which means it's ready for scientific interpretation. So we're sacrificing a little bit of computing on our side to eliminate that MPI dependency, and to present the data to the far end in the form that's desired by the analysis that the user has. And so this, producer-consumer model is a way of putting together a heterogeneous pipeline with one thing like that does the data reading, the LCLS streamer and PSANA, and then the processing code, which can be anything really. So PSANA is optimized for this heavily parallelized processing of single events, whereas the GPU does batches of events in continuous memory. And so the GPU, so when we built this original system, it was for CPU. Then came the GPU, and the GPU architecture is just different, right? And it's not portable. And so LCLS stream is a way of kind of letting the GPU do what it does best, handling that I/O threading and making sure that we are always doing the prefetch on the data and sending batches to the GPU so that the GPU is always busy and the fetching is happening behind the scenes. And when the GPU is ready for the next batch, it's ready to be pushed in. And LCLS stream can be used to do that, to sort of separate out the reading from the consuming. All right, one final word on NERSC, which enables this real-time analysis. What's really happening when we stream to NERSC is, we have a lot of local stuff happening in LCLS at the experiment steering. We transfer the data out to NERSC. And then there's a bunch of jobs that use the super facility API to use the super facility API to trigger a bunch of jobs at the remote site. Run in this example, it was on Quarry, but now it's Perlmutter. And so we can run a bunch of parallel jobs and then send the data back to our electronic logbook where the results can appear. And the goal is always to have this happen within minutes of a run ending. So if you acquire data for 10 minutes, a minute or two after the run ends, you want to have results. That's the goal. Okay. One other thing to mention is that there are other sorts of analysis, and Quinn has done quite a lot of work along with NVIDIA and Seshu to develop something called Numeric, which is just a plugin for NumPy in user code, but for performant GPU accelerated data analysis, and it speeds up the GPU analysis. But one thing I think that I learned is that even so, you still have to know about what's happening inside the workflow and inside the analysis itself. If there are a lot of for loops that don't use the GPU efficiently, then just substituting Numeric for NumPy isn't going to give you a magic speed up. You still need to do the work of refactoring the workflow to make it use the GPU in the most efficient way. So the goals of all of this, of course, is to accelerate scientific insight, to get to the answer, to the science domain knowledge as quickly as possible. AI is one way of doing that, and I didn't explicitly mention AI in here at all, but that AI, any algorithm can be running in any of the steps in the pipeline. So you need, the raw data and the data product are not the same thing. And so you need to do a lot of work before you get to the data product, and it takes both time, computing, and intelligence to do that reduction and get to the scientific knowledge. And right now, there are certain parts of this pipeline, and this is credit to Fred for the nice diagram where that question that is asked by the scientist that he or she is trying to convert into knowledge is a fairly slow moving system, whereas the experiment steering loop there is very time sensitive and happens very quickly. And in the before times, we had the luxury of having those time scales be roughly equal. So you could do the data collection, then do the data analysis, then do the data interpretation, and none of the parts of the system were slowing any other parts of the system down. But nowadays, when we have AI in the driver's seat, we have a lot more tools at our disposal for experiment steering. We can start beginning to contemplate self-driving experiments. And in that case, these loops are going to happen so much faster than human decision-making can happen. And so we need to kind of rethink the system and find a way to make this both loops keep pace with each other and make sure that we aren't relying on human intuition to make decisions that will then slow down the experiment. So I'm done here. This is my summary. And I think the one takeaway, if I had one takeaway for you, it is that every time, so we have this complex system, and I think we can all agree that's a lot. And that was really complicated. And every time a piece of hardware or software updates, changes, we have an OS update, new opportunity, new programming language comes along, AI ML comes up. Then the data system, the platform, the infrastructure, the hundreds of user workflows that are used for data reduction, fast feedback, data quality monitoring, decision support, data management, data processing also have to change. And I don't know if on my laptop, I can install an OS in a day and then I'm just irritated for like a week. When I do the same change in a facility, it takes me a year. And the user repercussions are felt for years afterward. So those timescales are not matching up. So that is like the big problem of the day, is for all the beauty of this system that we built to collect all of the data, get it to disk, and enable users to actually extract science out of it. It's none of it maintainable if it takes years every time I have to go from to Rocky 9, So the opportunities I will leave as an exercise to the reader, as are the challenges, and I will end here.
Thank you. I think we have time for maybe one or two questions.
So I'm Larry Kaplan from Hewlett Packard Enterprise. Thank you very much for the talk. Went by so fast. I definitely a lot of things I want to look at again. But one question that comes up, it's already so difficult to program the CPUs, the GPUs, the TPUs, accelerators, that kind of stuff. Can you say anything about the challenges of doing any of the ASIC and FPGA work? That strikes me as another level.
Yeah, I think we're very lucky at SLAC that we have the Technology and Innovation Directorate, and it's a team of people who are electrical engineers and they do a lot of that programming already. And say they are also building our detectors. So I didn't mention this, but we have a little incestuous relationship here with them. They build our detectors, so they have access to these FPGAs and these ASICs, and they are also interested in putting intelligence there. These are custom-built detectors. They are for us. They are for our purposes. So what can they do to make them better and more performant? And also, by the way, solve some of these transmission bottlenecks, because they're also having a hard time getting data out in an energy efficient way. So for me, the programmability challenge is really identifying the algorithms that are going to be most suitable at the edge. Like what's necessary for you in order to make a decision within microseconds or seconds, right? Those algorithms are the ones we want to promote in line, or the things that will give you better physics, right? Identify those algorithms and then find a way to make them fit into that itty bitty living space. Getting them, the itty bitty living space is defined by, how much memory you have available, how much, bandwidth, things like, and how many gates and flops you have available basically inside your FPGA. And that, is a known quantity. And what TID has given us is the SLAC neural network library. They've given us tools that allow us to program machine learning models and algorithms into those FPGAs, provided we can fit. Right. So my challenge is making them fit and make them performant and verify that they are not screwing up the science.
It sounds like you're able to take advantage of an embedded group that's familiar with this environment that allows them to be productive.
Yes, we are leveraging them.
Yeah. Okay.
That's the
Thank you.
Okay, so I think we should probably move on.
We can talk
Okay.
later if you want.
Yeah, we'll talk later.
Okay. Will you be around?
I'm around.
Okay. So you can find Jana later if there are more questions, and I think there will be more talks on FPGAs and detectors to